Okay, so now we want to finish this discussion about how we can form coproducts. So the thing is that this kind of pairwise arrow, which has this kind of singleton component, and this component which sends the things in A to this part of the power object, which looks like a sort of empty sub-object, or it kind of represents it. Well, this turns out to be monic. Now, the reason is because if we have a pair of arrows I and J from H to A, then we have that doing this kind of arrow after I, if we suppose that doing this kind of arrow after I equals the same thing we get if we do this kind of arrow after J, well then the first two components have to be equal. And so we have curly brackets I equals curly brackets J, but then since curly brackets is monic, that means I equals J. And similarly, of course, this other kind of arrow is monic, the one that goes from B to omega to the power of A times omega to the power of B, which has this pair of components, 0 subscript A exclamation mark B comma curly brackets. So if we form this kind of sub-object of omega to the power of A times omega to the power of B, given by this extension here, so it's the extension over Q of there exists X in A such that Q is curly brackets X comma OB, or there exists a Y in B such that Q is OB comma Y, where X in curly brackets denotes curly brackets X, then the thing is we're going to have that these arrows we just described are going to be in this kind of sub-object C. Why? Well, let's have a look at this one. Curly brackets, comma, OB exclamation mark A. Well, the thing is that if we have a look at this expression here, this is going to be true when we substitute Q for this with an A on the end. And then by theorem 16.10, we're going to have that this black arrow here is going to be in this extension. And in a similar way with the other black arrow. So basically, because of this, because we have 0A exclamation mark B comma curly brackets is in C, we can write this as C after I2. And similarly, we can write this as C after I1. So basically, we have our coproduct diagram, because this is the kind of situation we have. We have this big extension here that we defined as this sub-object C of omega to the power of A times omega to the power of B. And then we have these two black arrows into omega to the power of A times omega to the power of B given here. And then the fact that these are both in C give us these I1 and I2. And then this sort of source of this monomorphism little c, this thing I'm calling C underlined, this is really A plus B, and these are the injections into it. So this is forming the coproduct that we wanted. And we see from lemma 16.4 and so on that basically this is the same kind of coproduct that we encountered before. So for any pair of objects A and B, we form this coproduct with inclusions I1 and I2, which are monic and disjoint. And it's interesting that basically the way that we form this, like the critical thing, is really this kind of thing here, that we essentially just take the sort of disjoint union. But we do this by playing around with the exponential objects and using these kind of singleton arrows. And it suggests that we can do lots more kind of making new structures by sort of exploiting the fact that all this structure is existing in these power objects, and that we can sort of refer to it, label differently and so on, using things like singleton arrows, and then select sub-objects of it to define other structures. And Presumably that kind of thing can be done to make other new structures that haven't been considered in topos theory before. Maybe an NKS style approach might be interesting to find those kind of things. Anyway, onwards, kernel pairs. The kernel pair H, K, you think of it, well, one way to think of it is an arrow H from R to, so say we have an arrow, okay, let me start again. Say we have an arrow C from B to D. The kernel pair of C is this pair of arrows H and K. Say those both come from an arrow R, and then they're both going to go into B. And the idea is just that they'll form a pullback square like this. But there's another way to look at a kernel pair, because if we pair H, K together as an arrow from capital R to B times B, they form a monomorphism. And moreover, if we have a pair of arrows X and Y from H to R, then we're going to have X, Y is in this kernel pair H, K if and only if C after X equals C after Y. And that's another way of sort of defining what a kernel pair is. So anyway, I prove that such a kernel pair is monic here. So the basic idea is that if H, K after X equals H, K after Y, then we have Hx equals Hy and Kx equals Ky. And then drawing the Kx and the Hx on, we find the intermediary arrow can be X. And then we also see that we can equally write Ky or and Hy and find the intermediary arrow as Y. So X equals Y. And then we can prove that indeed the kernel pair does basically an arrow U, V into B times B from an object J is going to be in this kernel pair H, K if and only if C after U equals C after V. So I'll just show the argument on screen. You can pause it and read it. And then we can also go the other way around. So we can show that we can actually just define the kernel pair as this kind of sub-object of B times B with this kind of property. And then we can show that H and K also form this kind of pullback. So we can find this kind of unique intermediary arrow. We need to satisfy the universal property of a pullback. I'm calling that M here. So again, I'll just show this on the screen and you can pause the video if you're interested to see the proof. Okay, now equivalence relations. Twist is P2, P1. It's this isomorphism from A times B to B times A. Given a relation R, which we could write as H, K from a monomorphism from capital R to A times B, we define R op to be twist after R. We could call it K after H. So for an arrow X, Y from H to A times B, we have X, Y is in R if and only if Y, X is in R op. Here's the proof. So we call the relation R into B times B an equivalence relation if and only if identity B, identity B is contained in R. That is, we've got X, X is in R for every arrow X into B. And also, so that's saying that the relation is reflexive, but also for it to be equivalence relation, we need it to be symmetric and transitive. Symmetric means R op is contained in R, which basically means whenever X, Y is in R, we have Y, X is in R. And transitive means when X, Y is in R and y comma z is in R, we have x comma z is in R. And this kind of stuff happens for any x, y, and z coming from a particular object into B, and similarly this holds for any arrows x and y coming from a particular object H into B. So our next lemma, lemma 16.16, says that this relation H comma K, the sub-object of B times B, is going to be a kernel pair of this arrow C from B to D, if and only if we have, but it's always true, that CY equals CY dash is equivalent to saying that Y and Y dash are in this kind of relation here. So chi of H comma K of Y comma Y dash is true, which I think is fairly self-explanatory. It's just this kind of idea of the relation as the kind of, I mean, it's just this idea of the kernel pair as this kind of relation, which is picking out the kind of pairs of y's that have the same values when we do C on them. This is more interesting result. In fact, we use this to make our co-equalizers. So it says that for a equivalence relation H comma K of B times B, there is an epic little q, which is an epimorphism from B to Q, with H and K as the kernel pair for this little q. So how do we prove this? Well, basically, we form this arrow I, which is going to be the interpretation of the quasi-set of W of type B, such that chi of HK Y comma W. So basically you can think of this as mapping something in B. I mean, if you think about it in terms of sets, for example, it'd be mapping something in B to the set of stuff it's related to under this equivalence relation. And so the basic idea then is that if we do an epimonofactorization of such an I, we break it into a monomorphism I after an epimorphism little q. Well, let's let the target of this epimorphism be capital Q, then the thing is we're then going to have that H comma K is the kernel pair of this little q. And incidentally, this I here is basically the equivalence classes of our relation H comma K. And so you see it's the sub-objects of B such that there exists a Y in B, such that this sub-object is basically the stuff that's related to that Y under this equivalence relation H comma K. So basically, in this case, we can think of this Q here as sort of sending the stuff in B to its equivalence classes. So it's this epimorphism. And so this idea of things getting mapped the same way under Q is what's that's why this H comma K here that's forming this equivalence relation it's also going to be forming the kind of kernel pair of this epimorphism Q, which is essentially sending this stuff to its equivalence classes. Okay, next, lemma 16.18. Any epic is a co-equalizer for its kernel pair. So the idea here is if we have an epimorphism Q and we find its kernel pair H, K, then we can actually think of this Q as being the co-equalizer of those. Because it's essentially gluing together stuff that's, I mean, the idea of this kernel pair here is that it's going to be yeah, it's working, okay. So the idea of the proof, or at least a very rough sketch of the proof here, is that when we have this little Q is an epimorphism from B to capital Q, well, suppose it has this kernel pair H, K, and then just take some C such that CH equals CK, so this is like a candidate, and then we can define this relation V on Q times D such that chi of V of W, Z is equivalent, saying there exists a Y such that Y equals QY and Z equals CY. Now it turns out that V is going to be single valued and totally defined, so it's going to be functional. And that means there exists a unique kind of corresponding intermediary arrow, U from capital Q to D. So we have this kind of setup we like to have for a co-equalizer. So how do we construct co-equalizers more in general? Well, suppose we have, well, what we can do, we can define a sub-object epsilon of omega B times B. So it's essentially like a sort of sub-object of this kind of object of relations, if you like. And we can think of it as well, it's basically the equivalence relations. Okay, so you can read it here, but I mean, basically it's the relations, it's the variables little r of type omega to the power of B times B, where these relations are reflexive, symmetric, and transitive. Now, suppose we have a pair of arrows, F and G, from an object A to an object B. So we're going to say that a relation R on B times B respects F and G. If and only if for all X in A, we have that Fx and Gx are related. So given such an F and G, we'll define this sub-object R F of G of omega to the power of B times B to basically be the load of F and G respecting relations. So we can say that it's the extension of for all X in A, Fx, Gx in R over these relations R in omega to the power of b times b. Now, what we're going to do now is we're going to define another relation, rho, and this is a sub-object of b times b. And basically, this rho here is another equivalence relation. And it basically is going to relate a pair of things y and y dash in B precisely when they're are related for every equivalence relation which respects f and g. So this is really just analogous to the way that we form co-equalizers in the category of sets. It's just this sort of general sort of local set theory style approach. So, but more precisely than rho is this extension of for all r in omega to the power of b times b, chi of epsilon r, so that's this epsilon here, the load of equivalence relations, and chi r fg of r implies y comma y dash in R. So basically, yeah. So this is going to be another equivalence relation on B times B. And so let's write rho equals H dash comma K dash. And so since this is an equivalence relation, again, we can construct a Q from B to capital Q for this kind of rho here, basically the same way as we did in lemma 16.17, and this gives us the co-equalizer for f and g. So if you like, we can form this I here once again, which is the interpretation of the quasi-set of W such that chi of H dash comma K dash of Y comma W, it's this thing, this I is this arrow from B to omega to the power of B, and then if we do an epimono factorization of it, we get this Q, and this Q is going to be the co-equalizer that we're looking for. Also, just something to bear in mind, just a piece of notation which is related to this stuff. The quotient of an equivalence relation to H comma K is a co-equalizer of H and K, which has them as its kernel pair. And also a couple of notes from topos and local set theories. Suppose we have V as a term of type omega to the power of omega to the power of A, and then we can define this formula intersection over V to be the quasi-set of X of type A, such that for all U, variables U of type omega to the power of A, we have U in V implies X in U. And we'd also define union of V to be the quasi-set of X in A, such that there exists a U in a variable U of type omega to the power of A, such that X in V and X in U. And you can see that on page 83 of J.L. Bell's Toposes and Local Set Theories. So that's it.